All right, so last time we were working in section 5.1, and we're fairly close to the end of it, talking about integers, some different models for integer addition. And we had left off with a few properties right here, talking about adding and subtracting values that are integers in nature, and some results. Now, I mentioned this before I started this video, but these ideas of colored counters or this number line movement along the number line and everything are excellent concrete models for students as they're thinking about adding and subtracting integers. These are the shortcut kind of things that we do. And we do these and we start to develop them whether we're taught them or not. Eventually, if we worked with those colored counters or that number line enough, we would start to think, oh yeah, well every time when I take a negative number and another negative number, I will add them together and put the negative on the outside. That's the third one down here. The problem is that a lot of times that whole concrete step with those colored counters and the number line models is just omitted, and we jump to this. And when we jump to this, math starts looking like a bunch of rules. And it's really hard to remember all the rules when you're put under pressure, and so students make mistakes. So I hesitate to tell you that you should start right here. That's not probably a good place to start when you're teaching students about integers. Working with that hands-on manipulatives first is a much better starting spot for this kind of thing, and then these sort of fall out as you're working about that in that way. All right, the next one we're going to talk about is integer subtraction. So when we have subtraction, it looks something like this. All right, so for integers a and b, a minus b is the unique integer your book is using n such that a equals b plus n. And this is almost identical to the same definition that we had when we did whole number subtraction. The one difference that we don't have here is we don't have this contingency that says that we have a be bigger than b. We had to do that back with whole numbers because if we didn't have a be bigger than b, we could end up with a negative, and we weren't talking about negative numbers. We were stuck with the whole number system. So we don't have that sort of a disclaimer in there any longer. And one other piece of information to remember is that when we talk about a minus b, it's equivalent to talking about that as a plus negative b. I remember being in 7th grade and having a teacher talk about the fact that there's no such thing as subtraction. Emphatically, there's no such thing as subtraction. We all looked at her like she was off her rocker, right? But this is what she was talking about. She was talking about the fact that subtraction is really adding a negative. And so she was trying to hit home her point. Obviously she did, because I remember it, and this is quite a few years later in 7th grade. So this idea of adding a negative being equivalent to subtraction. All right, so just like last time, we're going to look at some concrete models for subtraction that we can work amongst instead of having sort of just some arbitrary looking rules or definitions as our starting place. And we'll have the same models. We'll have the chip model and the charge field model, and then in a minute we're going to have that number line model. All right, so the same thing as before. We start out with a circle, and inside our circle is going to be the first number listed, and the first number listed is 5, right? So what does 5 look like with chips? 5 black chips, right? So I've got 5 black chips. Now here's what's going to happen. Do you see this negative right here? We talked about subtraction in several ways. In fact, you guys on the ones that you're redoing still are doing a subtraction problem for comparison model, right? One of the models that we had for subtraction we talked about was takeaway. It's probably the most natural one. The idea that if I have something and I take some of it away, that's subtraction. Well, that's how we're going to interpret this negative here, the one in the middle that's not inside the parentheses, as removing something. However, it says I'm supposed to remove what? -3. And inside my picture right now, I don't have -3 because negatives look like what? Red chips. And I don't have any red chips in here. Okay, so is everybody with me so far? There is an inherent problem with the way this is set up currently. I don't have 3 red chips to take away. However, I can put red chips into my diagram, but I do it like this. If I put in, let me do it this way, a red chip, I will put in a black chip as a balance, because what is a red chip and a black chip combined to become? It's 0. So we talked about that last time, right? A red chip is -1, a black chip, is +1, so when we combine those, that makes a net total of 0. So I've added 0 inside this circle. I've done it in a funny looking way. I've added a red chip and a black chip, but that's net effect of 0. But now, so now I could take away 1 red chips, but I'm supposed to take away how many red chips? 3. So I need to do this same thing 3 times, right? So I'm going to have 3 additional black chips and 3 additional red chips inside of my picture. This picture now allows, and I could add more reds and blacks. I mean, there's nothing to that, except that I only need to add 3, right? I only need 3 red ones to remove, so I don't need to keep adding black and red chips to this, although it would be correct to do so. It would be okay to do so. It's just unnecessary. So when I'm looking at this now, I can actually remove or take away the 3 red chips. So these 3 red chips physically look like this. I'm going to circle them, and I'm going to drag them outside of this box. I've removed them. So then what happens is that my answer is going to be a circle. Whoops. And what's going to be inside my circle? 8 black chips. And then my answer is 8. So we have a way of removing a negative, and in essence, what did it do? It added 3, didn't it? So we can talk about the fact that the opposite of a negative right here, this subtracting a negative, really does end up being addition in a very concrete way with this particular model, instead of just sort of these definitions that we say minus a negative turns into a positive. It's not a terribly difficult one to remember, but it doesn't really explain what's happening when we say that. And this is a concrete model showing that. All right, so we're going to do that charged fields model, practice the same idea again. So I've got a circle. What's inside my circle to start with? 5 positives. And what does this notation, minus -3, mean? What's the first negative mean? Take away. I'm going to remove. And what is this -3 in this model going to mean? I need to remove 3 negatives, right? So this means remove, and the second part, the -3, actually means the 3 negative charges. I don't have any negative charges, so how do I introduce a negative charge into my picture? All right, right. So I'm going to balance by doing every positive, every negative, going to have a counterpart, right? I'm going to add 0 to this, and I'm going to do 3 of them because I need 3 negatives to be able to remove. And again, there's nothing special about the fact I'm using red. It's just a visual for you guys to see. You don't have to change colors on your work, okay? That allows me then to circle the 3 negatives that I'm supposed to be removing and flat out remove them. So that's this notation. Drawing this circle around them and drawing an arrow out is my physical representation for removing them from the picture. If you were working with the colored chips, I know this is back on the chip model, but if you were working with the colored chips, the kids would actually have all those chips there, and they would have taken them away, and they wouldn't see them anymore. So it's not like they've moved them outside the box and now they're on the table beside you or anything like that. They're just not there anymore at all. They have been removed. So my final answer then looks like a circle that has how many of what type of symbols in it? 8 positive charges. Any questions on that? What would happen if I had all negative charges left inside my circle? My answer would be negative, right? If I had all red chips or all negatives, I'd have a negative answer. All right, number line model and pattern model, same models as before, but we're going to do them now from a subtraction perspective. All right, so what in the world do these symbols mean on a number line model? All right, so this first negative that we've sort of interpreted from the other models as taking something away, in this model is interpreted as turning around. And I'm going to physically show you how this works in a second here. But this is turning around. And this -3 means that I move backwards. So the first thing I want to do is I want to show you what this does with your desks. I did this last time with the number line model, right? So I'm supposed to take, and I'll start over here with Lynn. Okay. So if I start over here with Lynn and I move 5 desks forward, I'm going to move 1, 2, 3, 4, and 5. I'm going to run out of desks here pretty much, okay? And I'm facing this direction. This is the direction I've been moving, right? The first negative means that I turn around. The second negative means I move 3 more desks, but I'd move them backwards. So I've got 1, 2, and then we've got a further row over here, 3, that we would be at. Can you picture it? It's hard to draw. That's why I wanted to show it to you in terms of me moving around in the room. So one of the first negatives is the idea of me turning around, and the other one is the idea of me moving backwards. Okay? So it would make me 8 desks away from the front of the room from where I started with Lynn. So in terms of a picture, it's hard to draw that, but let's attempt to do so anyway. So we're going to take this model, and we're going to draw a number line. And our number line is going to start at 0. And the first thing I'm going to do, so when I started over here at Lynn's desk, is I'm going to move 5 movements forward, right? 1, 2, 3, 4, and 5. So my first movement is 5 movements forward this way. Now, the equivalent of what happens next is that I move 3 more moves, right? Because I've turned my body around and I'm now moving backwards, which is weird, and there's no real good way to draw that. So our model actually ends up looking like we have this. So here's my 5, and here's my 3 moved backwards. I can't draw it, right? But could you physically work with kids on standing up and moving around a classroom in that way? Yeah, you could. But it sort of falls apart a little bit as we try to do the abstract picture on paper with it, unfortunately. So my answer's still 8, but I don't have a good picture to show it. Not all models really lend themselves well to paper and pen or an iPad, right? All right. Last model is the pattern model, and you guys, we did this one before. It was a good model for some of us. That's how all these models are, and maybe not so good for others, and that's okay. But for some people, this really establishes a good reason as to why this works. So if we're going to start with 5 minus 2. So we start with something that we can still concretely do with whole numbers. So what is 5 minus 2? 3. Okay, there's nothing special about me starting at 2. It's just where I chose to start. And then we're going to decrease the number by 1 that we're subtracting. So what's 5 minus 1? What is it? 4. Good. And then I have 5 minus 0. 5. So if you notice what's happening here, I'm decreasing each one of these by 1. And what's happening over here on the right-hand side? They're increasing by 1. So as I get to the next one, so it's 5 minus -1, I've all of a sudden encountered negative numbers that have a sort of a strange feel to them to us, and to say that I'm subtracting a negative is even weirder, right? So if I subtract a -1, you may know what the answer is from a variety of ways, but one way you can see it is from this pattern. If this went from 3 to 4 to 5, what should be the next value if the pattern continues? 6. So 5 minus 1 should be 6 because we've established a pattern that shows that it was for all the numbers before that. And we can continue that then with my 5 minus -2, which would then be 7. and 5 minus negative 3, which is the value we're actually looking at here, which is 8. Some kids really think in patterns a lot, and so this establishes something that they can sort of reason with very well. Any questions on that one? Okay, so let me reiterate one more time that it makes no difference that I started here with the number 2. I could have started here with 5 minus 3 or 5 minus 6. I just wanted something close enough that I didn't have to do this forever to establish my pattern. That was part of it. And I also wanted something that had a couple of steps before I ended up in the numbers that were negative. Does that make sense? That's the only reason I chose that number that I did. All right, one other piece of information in this section, and we have seen this, I believe, before in some homework problems and whatnot, but it becomes much more important as you're working with integers because these negatives interplay with things. So order of operations. You may have seen PEMDAS used before. Does anybody have an acronym that you used in high school or before? That's the most common one. There are a few others. Does anybody else come up with anything else or heard anything else? You had a song.
Yeah.
That's wonderful. Would you like to sing the song for us, Carrie? Maybe later? Okay, maybe later. All right, so mnemonic devices are really good for remembering things. This one's wonderful. Please excuse me, my dear Aunt Sally, or PEMDAS is great. But there is one flaw in the way that the wording or the acronym is done. And the flaw is that as we've sort of written it, it looks like multiplication comes before division and addition becomes before subtraction, doesn't it? Yeah, that's what it looks like. But it really doesn't. Okay, so let's first run through these and I'll show you what I mean by that. So what does the P stand for? This is parentheses. How about the E? Exponents. The M and the D are what? Maybe I should start out with the M on that one. Multiplication and division, and those are done interchangeably. I'll show you. And then what about the A and the S?
Addition, subtraction.
That's addition, subtraction. Okay, so anytime I get to something, I'll use the addition and subtraction example on this one. If I have this going on my paper, I don't know, I've got a whole series of additions and subtractions on here. If all I've got left is addition and subtraction, I move from left to right. I do not do addition before subtraction. And the same is true when I encounter if all I've got left or if I'm working on the step where I'm doing multiplication and division, I work moving left to right. So as we're moving from left to right, we can do 5 minus 3, which is 2, plus 2 is 4, plus 7 is 11, minus 6 is 11 minus 6 is 5. 5. We would end up with 5. So just to keep in mind that there's nothing special about the order of operations really saying that the addition comes before subtraction. And this works the same thing with the multiplication division. They're interchangeable. You move from left to right. Any questions on that? All right.